Okay, so hopefully we've got our three parts of our model now. We've got current, we've got potential difference, we've got resistance. We can put all these things together and we can start to apply them to real circuits, because mostly so far we've only looked at one component in the circuit, and obviously most circuits have more than one thing in them. So we're going to look at series and parallel circuits. We're going to try and use these models, and we've got to derive a general formulae for resistors in series and parallel circuits. So what's the total resistance of more than one resistor when we add them in series and parallel? And then we've got to try and apply this to circuits. Okay, we'll move on to more of that in the next lesson. Okay, so here's a couple of circuits just to look at. Hopefully we know this is a series circuit. The electricity goes through the first bulb, and then the same electrons have to go through the second bulb. So every electron is going through the cell and then both bulbs before it goes back to the cell, as opposed to a parallel circuit where the electrons are leaving and they take a choice here, if you like. They've got they can either go this way and go through this bulb, or some other electrons go this way through this bulb. Okay, so the electrons are going both ways. Okay, we notice in this one that the potential difference is shared because the electrons leave here with 12 joules per coulomb. They give some of them to this bulb and some of them to this bulb, but the total of these two must always add up to 12. In this circuit, then they give either all 12 to this bulb, or some different electrons go the other way and give all 12 joules per coulomb to this bulb. Okay, some people in GCSE think this is some kind of magic trick. I've got a 12-volt battery, but I'm getting 12 volts to this bulb and 12 volts to this bulb. But if you look carefully, you understand that there's 4 coulombs of charge coming past here every second. 2 go this way, 2 go this way. So in 1 second, 4 coulombs go through this cell, this battery, and the battery gives out a total of 48 coulombs, 48 joules of energy. This bulb gets 24, this bulb gets 24. But none of these meters are measuring the number of joules, they're measuring the number of joules per coulomb. Okay, so we need to look at these formulae for what happens when we put more than one resistor together. So here's our circuit. It's got 3 resistors in it, R1, R2 and R3. And we want to replace them with a single resistor R, which has the same effect of those 3. So the current flowing through the cell is the same in both circuits. Okay, well, what do we know? Well, we know from this circuit, V equals IR. In this circuit, this is where people go wrong. There's not V across each one of these. There's 3 different potential differences, V1, V2, V3. So we can look at this one here, and we can say for this part of the circuit here, this V1 is equal to I1, the current going through this one, times R1. Same for this one, same for this one, right? But we also know that these 3 potential differences add up to the potential difference that came from the battery in the first place. So I can substitute in here that V is IR, V1 is I1R1, V2 is I2R3, I2R2, V3 is I3R3. But hopefully you're already looking at this thinking, why on earth is he doing all these different I's? Because what do we know in this circuit? The same current is flowing all the way around, so these I's are all the same. So I1, I2, I3, I, they're all the same. So I can change all of those into I's, divide through by I, and I just get the total resistance is R1 plus R2 plus R3. You might even think that's fairly obvious. If I told you this was 10 ohms and 20 ohms and 30 ohms, you might say, well, obviously the total resistance is 60 ohms. However, in the second sort of circuit, you'll notice it's a lot more complicated. Okay, so here's our second circuit, just the same, 3 resistors in the circuit. We want to replace them with a single resistor, but the difference is that this time they're in parallel. Okay, let's apply the same thinking, V equals IR. Okay, so this one, if I want to know I1, then I1 is V1 over R1. I2 is V2 over R2, I3 is V3 over R3. Right, but this time these I's aren't the same, but we do know that the V's are the same. Okay, so we know that the total current here, the current that would have flown through this ammeter, which is reading the same as the one over here, is I1 plus I2 plus I3. So we can do the substitutions again. That's V1 over R1, V2 over R2, V3 over R3. But this time the V's are the same, so I can replace all of those V's with just V. We end up with this equation, and then we can divide through by V. Just be careful here, you don't just cross the V's out and end up with the same equation. This is 1 over R is 1 over R1 plus 1 over R2 plus 1 over R3. Right? It doesn't matter, you could do a general formula which would carry on for any number of resistors. Okay, but the very common trap is that people add these 1 over R's together, and then at the end of it they end up with the forgetting to do the inverse again at the other end of the equation. Okay, so here's some circuits to apply this to. Here's a nice straightforward series circuit, so hopefully it's fairly obvious that we just do R1 plus R2 plus R3, so 10 plus 10 plus 20 makes 40 ohms. So one 40 ohm resistor would replace these three. Here's a nice straightforward parallel circuit. So we've got 1 over the total resistance is 1 over 10 plus 1 over 10. Put down your calculator, it will say either 0.2 or it might say 2 over 10. But don't forget to then do the inverse. So if 1 over R is 0.2, R is 1 over 0.2, 5 ohms. Slightly trickier one because you've got two resistors that have got different values, but still the same method. Okay, 1 over 10 plus 1 over 20 is 0.15. Do 1 over that, we get 6.7 ohms. Okay, this is the sort of circuit where it starts to get complicated. This resistor isn't in series with either of these because every electron that doesn't go through this resistor doesn't have to go through the same one of these. They go one way or the other, but these two are in parallel. So you do the parallel bit first, just the same as the other one. So we get 1 over 20 plus 1 over 40 is 0.075. Do 1 over that. So a 13 ohm resistor would replace these two. A useful thing to notice is that the total resistance is always less than the smallest one. So when I start this, I know that this part is going to be less than 20. Then we've got a 50 ohm resistor and a 13 ohm resistor in series. So we just add those two together. We get 63 ohms. Okay, this one is not 4 resistors in parallel, it's 2 resistors in parallel, followed by 2 more resistors in parallel. So we have to do these two. 1 over 100 plus 1 over 20 is 0.06, 1 over 0.06 is 16.6, so 16.6 ohm resistor would replace these two. Then you do these two, do the same method, you get 18.75 ohms, add those two together, you get a 35 ohm resistor altogether. Then the last one, we've got these two in series. So we get an 80 ohm resistor to replace these two. Then the 80 ohm is in parallel with a 40 ohm. That gives us 26.7 ohms to replace this section. Add that to the 40, we get 67 ohms altogether.